Hi, my name is Nicholas Espinal. This is the 8th question from my Chapter 30 quiz, and this is what it asks. A closed loop conductor that forms a circle with a radius of 2 meters is located in a uniform but changing magnetic field. If the maximum EMF induced in the loop is 5 volts, what is the maximum rate at which the magnetic field strength is changing if the magnetic field is oriented perpendicular to the plane in which the loop lies? So to answer this question, we'll need to use a combination of Faraday's law and Lenz's law, which tells us that the EMF, induced EMF, is related to the negative change in the magnetic flux. And we also need to know that the magnetic flux is equal to the magnetic field times the area that it's passing through times the cosine of the angle that it makes with that area, also known as the dot product of the magnetic field and the area. And relating these two, we'll notice that the first line that we have here, Faraday's law and Lenz's law, say that the EMF is equal to the derivative of the magnetic flux. So the derivative of the magnetic flux is just the derivative of the magnetic field times A times the cosine of the angle between them, or the derivative of the dot product. So we have this derivative of the dot product, and since the area is not changing, A is going to be constant. And since the angle that the magnetic field is making with the area is 90 degrees, that means that they're perpendicular. If the magnetic field is perpendicular, then the angle between them is 90 degrees. So the only thing that can actually change here is the magnetic field. So this derivative is really just the derivative of the magnetic field multiplied by the area. So we have this, the derivative of the magnetic flux is just the derivative of the magnetic field times the area. Also known as the derivative of the magnetic field is also known as the rate of change of the magnetic field. So if we put this into our initial equation and replace the magnetic flux with this, we'll have the induced EMF is equal to the negative rate of change of the magnetic field multiplied by the area. And if the induced EMF is maximum, then the rate of the change of the magnetic field is also maximum. So this is going to be answering our question, which is asking for the maximum rate of change of the magnetic field. So we have this, and we'll have to solve for the rate of change. If we solve for it here, we'll have the EMF divided by the area is equal to the rate of change. Now we have the EMF is equal to 5 volts. The maximum EMF is 5 volts. The radius of this coil is 2 meters. That's what they tell us. They don't tell us the area outright, but we can find it just by finding the area for this circle. That's pi r squared. If we just have the radius, we'll be able to find the area of that circle. And pi times 2 meters squared is going to be the area. And we could put all of that into our equation. The sign doesn't matter. They just want the magnitude, the rate of change. So I didn't carry the negative there. But you'll see that if we just plug in our values here, 5 volts divided by the area, we'll get 0.39 Teslas per second, which if we round it up is going to be 0.4 Teslas per second. And that's going to be the rate of change of the magnetic field in this situation. So if we look at our answer choices, we'll see that 0.4 Teslas per second is the answer choice D, and that is answering our question. Thank you.